Sorry, let me, oops. Sorry, I picked the wrong screen to share. 1 second. I'm gonna do this one. Okay. Let's see. Slideshow.
We can see your email now.
Yeah.
Now is the presentation. Now it's
okay.
all right.
Perfect. Okay, so I'm going to be talking about the development of a strongly coupled thermo-mechanical model of permafrost for the simulation of Arctic coastal erosion. And this is primarily work done with Alejandro Mota, Jen Frederick, Charles Choens, and Diana Bull, who are colleagues of mine at Sandia National Labs. Let's see. Oh, here we go. Okay, so I wanted to start with a little bit of motivation for this work. The Arctic is warming at rates that are 2 to 3 times greater than the rest of the United States. This results in accelerated coastal erosion rates. So the figure on the right here gives you an idea of kind of what these rates are at various locations in northern Alaska. And you can see the rates are approaching 20 meters per year in certain locations shown here in red, with certain locations having lost as much as 200 meters between 2007 and 2017. So what's causing the accelerated coastal erosion? Well, the primary culprit is actually the loss of Arctic sea ice, which you'll hear more about in tomorrow's session. With the loss of Arctic sea ice, we see an increase in wave energy and storm surge. Basically, storms in the Arctic Ocean inundate the Arctic coast, causing thermal abrasive action, which removes parts of the coastline. And of course, increasing seawater temperatures and warming permafrost kind of exacerbates the situation. And so why do we care? Well, there are a lot of coastal communities up in the Arctic. People live up in northern Alaska, so those folks are threatened with displacement. There are also active Department of Defense sites, including toxic waste sites. So obviously, having this toxic waste kind of pummel into the ocean is a big concern for kind of the global climate system. And then finally, permafrost stores greenhouse gases, things like carbon dioxide, methane, nitrous oxide, which can be released into the atmosphere as the permafrost thaws and accelerate further global warming. So let me go into a little bit of detail about permafrost and some of the processes that contribute to its demise. So what is permafrost? I think this group probably is familiar, but in case there's someone online who isn't, what permafrost is it's essentially ground comprised of things like soil, rock, silt, clay, sand, held together by ice that remains frozen for 2 or more consecutive years. If you're looking at the northern hemisphere, about 24% of the northern hemisphere contains permafrost, so that's shown in the purple color in the map here. And if you're focusing on just kind of the northernmost regions, so Alaska, Greenland, Canada, Siberia, 85% of these areas sit on top of permafrost. So here I'm going to be focusing on coastal permafrost in the Arctic. And this type of permafrost turns out to be different from permafrost and permafrost present in other parts of the world. So in particular, kind of one unique feature of the Arctic coastal permafrost is that its predominant geomorphology consists of ice wedge polygons. So these are shown in the figure here on the left. So basically you have kind of these pieces of the soil, rock, silt, clay, sand mixture that are kind of interspersed with these ice wedges, okay? So the wedges here, they can grow and expand to be meters wide and tens of meters deep. And when you look down on the permafrost, if you're flying above it, let's say, here's how it looks like. So you actually see these polygonal patterns kind of, cut out by these ice wedges that you can see kind of marking the boundaries between these blocks. Okay. So with this sort of setup, what ultimately causes the permafrost to fail is the melting of the ice that's holding the permafrost together. Okay. So I want to talk a little bit more about how permafrost can fail. So there are kind of several different failure mechanisms, and I have 3 of them I've shown here. So the first 2, retrogressive thaw slumping and active layer detachment, these are typically caused by what we call thermodenudation. And what that is basically thawing of permafrost bluffs that proceeds under the influence of gravity. Okay. The third of these, block failure, is kind of similar, but in some sense different. So what happens here is basically, as the ocean kind of keeps hitting the bluff, you start to get a recess at the base of the bluff form, and this is called a niche. And so as this happens, you get this overhanging material, and if you get enough of the overhanging material, it will break off, and you get this block failure shown in the third picture. Okay. So the block failure is actually very important. It's the dominant failure mechanism in many sites in northern Alaska. As you can imagine, it can actually cause pretty rapid permafrost loss. So these blocks can detach and disintegrate in as little as a week. And I have some images here that kind of highlight this. So these were done from a 2019 UAV survey performed by Ben Jones, who's a collaborator of ours from the University of Alaska Fairbanks at the Drew Point site in northern Alaska. And you basically see, the breakup and the break off and kind of disappearance of these rather large blocks in just a total of 13 days here. So just quickly going back to the previous slide, one of the reasons I showed this was in developing a permafrost erosion model for the Arctic. We're really looking for a model that's going to be able to capture all three of these failure mechanisms, not just a particular one. And it turns out that that's kind of lacking in earlier models of permafrost that are out there. Okay. So I think that's kind of a nice segue into the next slide. How permafrost erosion is typically modeled. So when this project began in 2017, tools to accurately predict Arctic coastal erosion did not really exist. So existing models, including models coupled to the Earth system models, were fairly primitive. Many of them based on trend projections or empirical relationships. There are some PDE-based models out there, but most of these are thermal models. So in particular, they don't account for the mechanics and deformation of the permafrost, which is actually important, especially if you're looking at this block failure that I showed. Another deficiency of some of the older models, they typically use fairly crude estimates of oceanic boundary conditions, and they also don't typically account for geomorphologies or geophysics of the permafrost. So that's kind of where this project comes in. So let me tell you a little bit about the project. So the project is known as ACE, which stands for Arctic Coastal Erosion. This is a project in its third and final year, and it's funded by internal Sandia LDRD program, which stands for Laboratory Directed Research and Development. And this is basically a pot of money for more kind of high risk, high reward type of projects that are maybe more exploratory in nature and need to be matured a little bit before they're considered viable for other sorts of funding. So the aim of the ACE project is to try to change the state of the art in permafrost erosion modeling by creating a field validated predictive model of thermoabrasive erosion for the permafrost Arctic coastline. And we're taking a physics-based multi-scale approach in this project. And so this is illustrated on this slide. I'm going to focus on kind of the top box here, which is where what we've been working on as a part of this project, and really kind of the bottom part here is going to be follow-on work as it turns out. But essentially what we've been focusing up until now is the development of a micro-scale multi-physics finite element model of Arctic coastal processes. The idea here is to create a model that will make it possible to simulate small subregions of the Arctic coastline that are tens of meters long and wide. And kind of one of the really key features of the model is that it's designed to capture 3D heat transfer together with mechanics-based plastic deformation, something that hasn't been done before. So another kind of goal and something we've really been able to accomplish, I think, with this is also to create a model that will take in much more realistic boundary conditions from from actual wave circulation data that represents time varying realizations of individual storm events. So I'll go into a lot more detail of about kind of all the different pieces here in the coming slides. Just to give you an idea of the big picture, admittedly, this microscale model is going to be too expensive to model the entire Arctic coastline. So the idea would be to take this model and ultimately upscale this into a mesoscale model and a macro scale model that would allow you to simulate larger regions and would be amenable for integration into the E3SM. And like I said, that's going to be in a follow-on project, and I'll talk a little bit about that project at the very end of the talk. Microscale model, that's kind of what I'll focus on for the remainder of the time. So the cartoon here illustrates the various components comprising our microscale model. And it's really meant to show you kind of what are the relevant pieces and how are they. So you can see we have kind of 4 key pieces here. What are the pieces? So we have the sea ice ocean wave model, the ocean circulation model, the permafrost thermal model, and the coastal erosion model. And so the way this is intended to work is the ocean wave model, which for us includes sea ice cover, feeds boundary conditions to the ocean circulation model. The ocean circulation model is used to predict nearshore currents and their interaction with waves along the coastline. And then the ocean circulation model provides boundary conditions to the permafrost thermal model, tightly coupled with the erosion model. And so the erosion model is going to predict how your permafrost will erode and change and pass that information back to the circulation model to be redistributed back into the environment once we're connected to an Earth system model. So for us, the sea ice ocean wave model, this is WaveWatch 3. So that's a model developed by NOAA. And the ocean circulation model, this is the nearshore model known as the SWAN model, which is tightly coupled to the Delft 3D model. This is developed by the Delft University of Technology in the Netherlands. So I'm not going to go into really any details about the oceanographic model, except for to say that it's going to provide boundary conditions for the terrestrial model, which is going to be the subject of this talk. But I just wanted to recognize here, and I'll touch on this later on, but this project actually goes way beyond just the terrestrial modeling. We had collaborators developing this oceanographic, model at Integral Consulting down in Santa Cruz. Conditions for this model, and we also had some experimental work in a field campaign as a part of this project that I'll touch on a little bit when I talk about calibrating and validating the terrestrial model. Okay. All right. So let me kind of, before I get into the details of the finite element thermo-mechanical model we've been developing as our terrestrial model, I wanted to discuss a little bit the anatomy of a canonical computational domain for one of these problems. So the slide shows a representative domain. So you can see this is 30 by 30 by 5 meters. So that's going to be characteristic of the domain sizes that we're targeting with the microscale model. You can see this is comprised of these hexagonal polygonal wedges shown in gray. And these are intersected with the red, which is representing these ice wedges that I showed earlier. Okay. So we're going to call this thing the bluff, just defining some lingo. And the front part that's exposed to the ocean, where we're going to have the oceanic boundary conditions, that's going to be called the bluff face. And basically, this is just a kind of a simplified geometry that's meant to represent the actual geometry of one of these, coastal regions where you get these polygonal blocks that I showed earlier. Okay. So let me talk about the equations we're going to solve in this canonical computational domain. So we have a thermo-mechanical model. I'm going to start with the mechanics part. So the variational form of the mechanics equations is obtained by minimizing this energy functional phi in the purple box. So if you're a solid mechanics guru, this will look very familiar. If you're not, it probably won't. But it's not so important kind of what all the pieces here are. So the important things are as follows. So this is a PDE-based model. Okay. We're going to solve these equations for the permafrost displacements and the new eroded computational geometry. And so I'll talk about how we do the erosion on the next slide. And then what's embedded in these equations is a material model. And so we're postulating here what's called a J2 constitutive model for both the ice and the permafrost. And this is the simplest model with plastic behavior that we both know that we know both permafrost and ice exhibit from experiments that have been done on those materials. Okay. Symmetry boundary conditions on the sides, that's not too interesting. This last part is very important here, the last bullet. So this is the expression for the yield stress. So this is also part of the model. And this is something that we postulate. So this can be changed based on our understanding of the permafrost and how it erodes. But essentially what we're saying here is that the yield stress of the permafrost depends on the yield stresses of the soil and ice, the soil ice volume fraction, and the ice saturation. Okay, and this is going to be important because this plays into our erosion failure criteria, which I'll talk about on the next slide. Okay, so an important feature of our mechanical model is that it allows for the simulation of erosion by actually removing elements from the computational domain. And that's done based on several failure criteria, which are listed here. So the first material when it reaches a critical exposure time to water. Okay. The stress material, this removes material when it reaches a critical value of the yield stress. So that's this expression here on the previous slide. And then the last one is the kinematic criterion. And this basically just removes material when it has tilted excessively, kind of like the picture shows here, assuming that in that case, it will have fallen off as a part of block erosion. And this has the added benefit, if you put this, of kind of improving the numerics of the simulation, because if you keep this tilted material around, it can kind of mess up the performance of the solvers that we have. Okay. So I emphasize that we're actually removing material from the mesh. So this is a really simple animation that shows this, and I'll show more sophisticated ones later. But we start with an uneroded geometry. We start, as we apply boundary conditions, the elements get removed, and eventually we see the formation of this niche at the bluff face. Okay. All right. So that was the mechanical model. So let me now talk about the thermal model, which is the other piece of the overall model. So the thermal model is in the yellow box. So we basically have a transient heat conduction equation in a non-homogeneous porous media. And we're going to solve this for the permafrost temperature and use that temperature to define the ice saturation F. Okay. And you can see we have a lot of different parameters here, density, specific heat. There's a mixture model that takes into account the fact that we have different materials. I'll touch a little bit about where these come from in I think the next slide. But something worth mentioning is that we have this theta tilde term in the inertial part of the equation. And so this is important because this is how we incorporate phase changes. Okay, so the ice can go from water to ice, liquid to solid. So the way we take that into account is through what's called the soil freezing curve DFDT. And this is basically a curve that's only non-zero in a very narrow band, kind of near -1 Celsius, where you're going to have the phase changes. And so the thermal model is where kind of all the interesting boundary conditions are applied from the wave model and from atmospheric data. So we have local geothermal heat flux from below, mean annual air temperature from above, and then air and ocean temperature applied at the bluff face. Let's see. Okay. So I wanted to talk a little bit about where the parameters and other inputs in these thermal and mechanical models come from. And I think this really kind of highlights the breadth of this project, which is, like I said earlier, kind of goes way beyond just the computational. So I'll start with the mechanical parameters. When we started this project, what we found is that there was really limited data for mechanical parameters of permafrost out there in the literature. So my colleague Alejandro on this project was able to convince the PI to actually have a set of experiments performed on frozen soil samples at different temperatures and having different ice contents in order to estimate some of the parameters in the model. So this would be things like strength, Young's modulus, Poisson's ratio, porosity of the permafrost, things like that. And so these were done by Charles Choens at Sandia's geomechanics laboratory down in New Mexico. And the samples came from Drew Point. So that's where the star is up in northern Alaska. That's just the location we're currently targeting with the microscale model. In terms of other parameters, so some of the parameters come from the literature, densities, thermal conductivities, heat capacities. The boundary conditions come from these wave models that I mentioned before, the WaveWatch 3, Swan Delft 3D models. And then another kind of important thing I wanted to emphasize is we also have observational data that we're using. So some of this data was collected by our collaborators at University of Alaska Fairbanks and USGS. We have UAV data that's not listed here, but I showed some images earlier. We use USGS weather station data. We use some borehole data from Alaska as well. And then in August of last year, some of the team members at Sandia, who typically actually do computational work, went up to Drew Point and collected measurements of various things like polygon dimension, ice wedge thickness and depth, bluff height, living organic layer thickness. And this is Jen, my colleague, who is actually measuring a niche up there at Board Point. And fortunately, I wasn't a part of the team yet when they did this, so I didn't get a chance to participate. It would have been a really interesting experience. Oops, oh shoot, what happened? Sorry. So just putting everything together, what we end up with is a coupled thermomechanical formulation. So initially, we were looking at a monolithic solve involving the mechanics and the thermal equations. More recently, we've switched gears to look at a more sequential coupling. So that's what's illustrated on the slide. And I think it's kind of more instructive because it shows you kind of what model needs what. But we're changing to this because of some numerical issues that we encountered with the monolithic approach, and I'll touch on that when I show results. But essentially, the way this works is the thermal model is solved for the temperature. It's used to define ice saturation. Ice saturation gets passed to the mechanical model, which computes displacements and the new eroded geometry. The eroded geometry gets passed back to the thermal model, and this repeats. Okay. And so one, I think, unique characteristic of this approach is the coupling happens at the level of the material model. So this ice saturation, this gets fed kind of deep within the material model that defines the mechanics equations. Okay, so that's just a really just a much tighter coupling than other couplings that you can conceive of when coupling these two equations, sets of equations. Okay. So I'm going to show results for the model. So let me talk a little bit about the implementation. So the ACE model is implemented within the Albany LCM code at Sandia. So this is a open source parallel C++ multi-physics finite element code available on GitHub at this URL. Okay. Some of its salient features, it has a component-based design for rapid development where many of the components are Trillino's libraries. These are also open source libraries available on GitHub. And we picked this code because it's really very strong in both solid mechanics and climate. Okay, so we had a big project called LCM, Laboratory for Computational Mechanics, within this code. It has a wide range of constitutive models, including the one we're using. And then we also have a long history of doing climate in this model. So we have the Albany land ice component, the OLLI model, which is the land ice component of the DOE E3SM within Albany. And some of you have heard me talk about this in the past in this session and other sessions as well. Okay, so let me show some results. So the first set of results are for a mechanics only simulation. And these were generated before our thermomechanical model was ready. And these are from a special issue of Frontiers in Earth Science. So here's the paper if you'd like to look it up for more information. It just came out last month. So a little bit about the problem setup here. The idea was to have a set of 3D mechanics simulations aimed at assessing the impact of the bluff geometry and material variability on the stress states leading up to bluff failure. So you could think of it as a sort of a kind of crude sensitivity study. This is a mechanics only simulation. We're primarily looking at block failure due to gravitational loading. So the only loading we had here was the gravitational loading. And the main quantity of interest we're looking at is the location and magnitude of sigma T max, the maximum tensile stress. Okay. So in the interest of time, I'll just kind of focus on the main takeaways from this. The first takeaway is that of the various parameters we considered, so these included bluff height, ice wedge polygon size, ice wedge geometry, bulk density, Poisson's ratio, I believe some other parameters too. The parameter that had the largest effect on maximum tensile stress, sigma T max, was the niche dimension. Okay, so these pictures are showing you 6 different erosional niche heights that range from 0.1 to 3 meters. And the stars indicate the value and location of the sigma T max. And basically what you can see is that it's these shorter and deeper niches that were more likely to fail. Okay, and that's probably consistent with what you would kind of intuitively expect. And these bottom two were the ones for which the sigma Tmax exceeded the lower bound for tensile stress from lab measurements of 100 kilopascals. And so the shading here just shows you kind of potential failure areas, kind of what's going to break off, essentially. So these are basically the same results as on the previous slide, just visualized in 3D to emphasize that this is a 3D simulation. So on the left, you can see that as the niche advances into the block, you get this overhanging section of the block that acts as a cantilever. And then on the right, this is showing the XX component of the Cauchy stress tensor is a function of the distance from the back of the bluff. And basically the highest tensile stress happens kind of where the cantilever meets the rest of the block, again, kind of as you would probably expect. Another thing we looked at here was the effect of tension cracks on block failure. So basically observations have suggested that failure can occur along tension cracks in the ice wedge polygon centers. So that's shown in the set of images on the right. And just in the interest of time, I'll just summarize the main takeaway here. So basically we were able to confirm that these tension cracks can form within the range of niche depths and heights that we considered and can contribute to the localization of this strain and ultimately failure of the permafrost. Okay, so let's now look at the thermo-mechanical model. So I'll first show a really simple proof of concept setup that we call the cuboid problem. This was just kind of a verification that we did before getting to more realistic problems. So this is the geometry. It's a cuboid comprised of a block of ice material that's wedged between two blocks of permafrost material. And we're going to heat this and stretch it from the top and initialize the temperature to 265 K, which is below the melting point of ice. And so what I'm going to do is I'll show, I think it's only one animation actually, but I'm going to show, I'm going to take a line down this ice wedge, and I'm going to plot along the line the ice saturation, the water saturation, and the temperature. Okay. So initially ice saturation is 1, water saturation is 0, temperature is 265. So this is all consistent with the ice being frozen. And then as the simulation progresses, what happens is, this gets heated, the heat propagates down. So the temperature of the ice starts to go up from the top. And then as that happens, the ice saturation goes down, the water saturation goes up, which suggests that the ice is melting. Okay. And so this is a movie that shows you the simulation. So the temperature is on the right and the ZZ component of the Cauchy stress is on the left. So this is just highlighting the coupling, okay? So this is in the mechanics equations, this is in the temperature equations, and as the heating kind of propagates down, you see that the stress is maximal in the middle, which tells you this is where things are going to fail. That's exactly what actually happens. Okay, so the last case is a kind of moving towards a more realistic problem. So we call this a 2.5D slice problem. So the idea here is we take the canonical domain that I showed earlier, and we're going to cut out a 2.5D slice. So here's how it looks like. And we're going to perform a thermomechanical simulation on this geometry using some realistic boundary condition data from 2011. So here's some of the data, air temperature, ocean temperature, and water height. And ultimately, we'd like to use some of the realistic material properties from the laboratory experiments that I mentioned. But in this initial study, we're just assuming the bluff is comprised of only ice. Okay. So some results. So here, the idea is to use the thermomechanical model to try to simulate erosion during the summer months. So, the goal is to do a 3 to 4 month simulation starting in early May. And the results I'm going to show here are for the tightly coupled implementation of the model, where we're solving for the displacements and the temperatures monolithically. And this is for a 0.2 meter resolution of the problem. So what's shown here, this is the Z displacement. And so what you can see is the model is able to run for 22 days and to perform 26 erosion steps during this time. And as the simulation progresses, you get this small niche kind of formed towards the bottom. And if you zoom in on it, you can see we get this overhanging material that kind of droops down, similar to that mechanics only simulation with the cantilever that I showed earlier. This is showing the XX component of the Cauchy stress tensor. So what this basically shows you is kind of where the failure is going to happen, where cracks are going to initiate. So you can see that the highest stress is kind of near the corners of this niche. So that tells you this is where we're going to have cracks. And again, this is consistent with what you would expect and what's actually observed. And finally, the temperature. So this is meant to show you just that what's driving this is the boundary conditions, the atmospheric boundary conditions up here, and some of the oceanic boundary conditions at the bluff face. Okay, so that all looks, very promising. We do have some issues we need to resolve with this. So some of the issues are listed here. So one of the issues is the results are very mesh dependent for this problem from what we've seen. So this is a movie that shows you what I mean by that. So these are two different resolutions. So 0.2 meter resolution, 0.05 meter resolution. You can see that the patterns are very different, and this is with the same boundary conditions. So that's something we're trying to understand. Another issue is that for the finer resolutions, we get these teeth-like patterns at the bluff face. That's something else we're trying to understand. This does not seem to be physical, so we're trying to see if this is maybe due to how the boundary conditions are applied or how they're processed. Another issue is that regardless of the mesh resolution, we have not been able to get this to advance beyond 22 days. So what happens at 22 days is basically the nonlinear solver starts to stagnate and fail. And we do have a theory with what's happening here. So we think this has to do with the monolithic coupling of the temperature and the mechanics equations. The equations have really different scales, so that can really kind of hamper convergence. And that's really kind of the main motivation for moving to the sequential thermomechanical coupling approach that I described earlier on. Okay. So I'm over time, my apologies. Let me wrap up. So I talked about the ACE thermomechanical model to simulate transient niche development and permafrost erosion within Albany. We're calibrating the model using realistic observational and experimental data and realistic oceanic boundary conditions. And there's still a lot of work to do. So the main priority right now is to resolve these issues with the coupled thermomechanical model that I showed on the 2.5D slice problem, where we're pretty optimistic about that sequential approach helping just from past experience. So we're working on that right now. Once we're able to run the model longer, we plan to look at things like integrating chemical transport into the model, realistic erosion calculations using the model, as well as doing some tuning, sensitivity, and validation runs. And longer term, the goal is to use the ACE model to understand coastal processes in the Arctic and to upscale the model into a meso and a macro scale model that would allow you to simulate larger regions and be amenable for integration into the E3SM. And we are going to have the chance to do this, fortunately, through a newly funded DOE project known as Interface. I think some of the other speakers in the session are affiliated with that, but it's going to be a project that's focusing on modeling and understanding coastal processes in the Arctic, and the ACE model is a member of that project. So references, the red ones are the ones that came out of this project. And I'll, before I end, I just wanted to acknowledge our collaborators on the project. So in addition to the co-authors I had from Sandia, we have collaborators at USGS, University of Alaska Fairbanks, Integral Consulting, and University of Texas Marine Science Institute. So they're listed here by name and shown in the photo. So I'll stop here.
Thanks, Irina. That's a very interesting talk.
Thanks.
Do we have any questions?
Irina, I have a question on the nice talk. I have a question on the temperature solver. I had to miss a couple of slides, so you might have mentioned that already. So I'm curious how you handle the fact that you have water and ice and at the same time.
Yeah. So let's see. Let me go to the slide.
Sorry if you
okay.
went to.
No, it was fast. There's a lot of material here. Oh, here we go. Yeah. So it's done through this inertial part of the equations. It has this theta tilde term, and so that has what we call the soil freezing curve. And so that's a function. It's actually the derivative of the function shown here, but it's basically a function that's only non-zero in a very narrow band near -1 Celsius. So that's how the phase changes go in through this term in the equations.
I see.
Yeah, we can talk more maybe offline, but there's a lot of details there. But it's effectively that expression that handles the change.
I see. I see. Thanks.
Any other questions? So I guess I have one real quick. So for the next set of calculations where you're doing the thermal and the mechanical kind of sort of not all together, but iteratively, yeah, sequentially. So are you going to be using the block that you showed originally, or more of that narrow thing you showed for the coupled thermomechanical? What is the domain you're going to be using for those?
So I think we're let me see. So we would start with the 2.5D slice, just because that's
okay,
kind of the simplest. So the idea would be to try it on this just ice only geometry, see if we can resolve those issues, and then we would kind of make it more and more complex. So we would put in the material properties to have the permafrost, and then eventually we would go to this 3D geometry. We do have data for this. And so the intention was to try this, and still is ultimately, but we're sort of trying to resolve things on kind of the simplest problem. That's the simplest but most realistic problem where they show up. So like for that cuboid problem, we don't have any issues like we see on this problem. So so initially it would be this, but then we would go to the more realistic 3D geometry, certainly as a part of the next project.
Thanks. That sounds good. So I see Jan mentioned in the chat that we have extra time if we want to have additional discussion. So I just want to open it up if there are more questions for Irina or for any of the other speakers from the audience. Well, if we don't have questions, maybe I'd ask everyone to unmute, and let's thank all of our speakers. Clapping, applause or something. Everyone.
Thank you.
So appreciate everyone attending the session.
Yeah, thanks everyone.
Thank you.
So next there will be a poster session which you can attend. So everyone, thank you. It was really interesting.
Thank you, Jan, for hosting.
Yes, thank you.
Yeah.
Okay, so have a nice day and bye.